So the final section of this professional development is whole number addition and subtraction. Our text that we've been using to develop this suggests that problems involving addition and subtraction are a good context for learning place value. So in other words, using addition and subtraction to teach place value is an effective method rather than just teaching concepts of place value on its own. And students often, when they only understand the digit by digit procedure of adding and subtracting, they're making errors and they're not able to make accurate estimations of what the answer should be. Knowing the place value of it gives you some background to make an accurate estimation of what the answer should be and helps students arrive at the accurate answer. So there are a few different main topics that we will cover as part of this section of the professional development. The first being that there are 3 types of computational strategies. So the first being direct modeling. It is what precedes any invented strategy or algorithm that students will learn on their own. And it's mainly taught through the use of manipulatives or drawings. So later on in this professional development, I will model how to use manipulatives and drawings to teach whole number addition and subtraction. This does not mean that you should avoid giving them problems involving 2 digits, because you can certainly do 2-digit addition and subtraction with manipulatives like base 10 blocks or tens frames or drawings. But rather that work with students that are still struggling, seeing a 10 as a unit, suggests that you should have a tool that allows them to see a 10 as a unit. The next type of computational strategy are invented strategies. So an invented strategy refers to any strategy other than the standard algorithm, or that does not involve the use of physical materials or counting by ones. So this is when you move from using manipulatives and drawing pictures and just working at the ones unit level. But you aren't quite yet to that standard algorithm of borrowing and carrying for regrouping, but you are still working within those place value concepts. So the way that this has been described by the Common Core state standards is that based on place value properties of operations and or the relationship between addition and subtraction. So you're looking more at the relationship those 2 operations have with each other. You're looking at the place value and the properties of those operations. But it sets the expectation that students are able to develop, discuss, and use efficient, accurate, and generalizable methods to compute sums and the properties of operations. So you want them to be using strategies that they can use over and over and over again, that aren't just going to work for specific problems. And we will get into more of those strategies later on. These invented strategies and how they contrast with a standard algorithm. So invented strategies are number-oriented rather than digit-oriented. So you are focusing on the number as a whole and what that number means, not just the digit in that place value. So think of a problem like 54 plus 26. You are thinking of 4 plus 6 and 5 plus 2. You are not thinking 4 units of 1 plus 6 units of 1, and then 50 plus 20. You're thinking of those individual digits, and that's kind of what the standard algorithm is focused on, is just thinking of a single digit in that section. But when you look at an invented strategy, you look at the complete number. So instead of 326 for 326, you would be thinking 3 groups of 100 or 300, 2 groups of 10 or 20, and 6 groups of 1 or 6. So typically invented strategies are left-handed rather than right-handed. So when we think of the classic algorithm, we start on the right side with the smallest numbers. With an invented strategy, you can start with those bigger groups of numbers. And then invented strategies are a range of flexible options rather than one right or correct way. So standard algorithm, there's really only one way to do that for addition and subtraction. Where invented strategies, there's multiple ways and they are more flexible. There are several benefits to using invented strategies over standard algorithms, and these would be the things that I would use when parents ask, why Common Core? Why all these steps? Which for most teachers, that is a question you will get over and over and over again. So really being able to describe why we use these strategies versus just doing the standard algorithm is important. So with invented strategies, students typically make fewer errors. And that is proved with research that reveals students using methods that they understand make fewer errors. I don't know about most of you, but when I was learning the standard algorithm, I could not tell you why I carried a 1 or why I borrowed a 1. I just knew that's what I was supposed to do. So when students understand what they are doing, they make fewer errors. There's less reteaching required. Their students develop the number sense required to perform these operations. So they use number-oriented, flexible algorithm, and it offers a larger understanding of the number system. Typically, students who move to the standard algorithm too early aren't able to explain why those standard algorithms work. Whereas a student who started with an invented strategy and then moved to a traditional algorithm can tell you, oh, I was regrouping a group of 10s into a group of 10 ones. Invented strategies are the basis for mental computation and estimation. So like I was saying earlier, you can't estimate what the answer should be if you're just looking at those individual digits rather than the number as a whole, because you don't even know what ballpark you should end up in. And when you're doing mental math, the standard algorithm can be quite lengthy and a little bit disorganized. Whereas if you think of invented strategies, they're a little bit more flexible, and you can think about them in ways that are easy to do with mental math. Flexible methods are faster than the standard algorithm, which a lot of people would argue with, but once a lot of those steps can be done mentally once you've done them multiple times. Whereas if you're doing 4-digit addition and subtraction with an algorithm, it can get very disorganized very quickly. You can make simple mistakes and it does take a while. The algorithm invention is itself a significantly important process to doing mathematics. So the process of getting to that algorithm is just important as learning the algorithm itself. And then invented strategies serve students better on standardized assessments, because there's going to be a strategy that they can pull out and use for that if just that one single choice of a standard algorithm is not serving them well. The next component to this, the next computational strategy would be mental computation. And just as I said before, the invented strategies model really works its way into that mental computation. So mental computation is a strategy, is simply any invented strategy that is done mentally. So it takes a while to build to be able to get there, but if you learn invented strategies first, you will be better off in the long run when you try to do mental computation. So there are three primary components when we get into the standard algorithm. The first is knowing the step-by-step procedure and how it is performed. The second is knowing why the algorithm works and how it can be applied. And again, you can't know this if you skipped the invented strategy phase. And knowing when an algorithm should be used and comparing the value and usefulness of different algorithms. The focus on teaching standard algorithms should not just be a memorized series of steps. We need to teach students why those steps work and what the purpose of each of those steps are. So our Common Core standards do have the standard algorithm listed as a necessary component to learn, but doesn't really start until 3rd or 4th grade. And a lot of those algorithms aren't even taught until 5th grade. So it's important to really put a heavy emphasis on those invented strategies at the younger grade levels when they're learning those foundational concepts of place value and number sense. In order for a standard algorithm to be used accurately and effectively, it has to be understood. And I know a lot of times I've had students come in here and say, hey, I learned this really cool trick. And come to find out they had a parent teach them the standard algorithm at home, which there's nothing wrong with that. But it is important to emphasize to those students why it works. And oftentimes we don't touch on that until higher grade levels when they're learning it for the first time. So it can be challenging because they haven't developed all of those invented strategies first. But standard algorithm is another tool they can put in their toolbox. So eventually it is something that they will learn. Students are unlikely to land on the standard algorithm as an invented strategy on their own, but it will be neat. You will have to introduce it and explicitly teach it. So explicit instruction is such an important component of math instruction, and that applies early on. It's also important to note that the standard algorithm isn't so standard. Different countries do it differently. So that if you work with a lot of migrant students, that is an important thing to know. Also, I think it's important to note that the environment that you teach in, students need to feel safe to develop those invented strategies, meaning that they need to be able to try and make mistakes and be walked through the development of those invented strategies, and that will ultimately lead to a better understanding of those strategies. So some big things to keep in mind: avoid immediately identifying the right answer when a student states it. give other students a chance to consider whether they think the answer is correct. Um, expect and encourage those student-to-student interactions. Um, encourage students to clarify previous knowledge and make attempts to construct new ideas. Promote curiosity and openness in trying new things. Talk about both right and wrong ideas. By looking at those wrong ideas, they can better understand the correct ideas. Move unsophisticated ideas to more sophisticated just through instruction and modeling. Use familiar context and story problems. So story problems are a great way of teaching all areas of mathematics. And if you are using context that's important to them, it's going to be more motivating, more relatable. And then show samples of student work anonymously so that students can critique that reasoning, and it'll help them build up their own repertoire of strategies. And they will be better able to explain those things.